Silicon is made from ordinary quartz sand, and rods of silicon are then created, or drawn, at extremely high temperatures. Thin slices are then sawn off these rods with great accuracy. The ICs will be produced on these slices of silicon, for which purpose the slices will undergo 300 to 400 processes. The first step in the production process is as follows. In this special oven, the slices are covered by a new thin layer of very pure silicon, into which the transistors and other components can be built. The slices with a new layer of silicon are placed in other boxes, where the silicon is allowed to oxidize. This insulating oxide layer can be removed at a later stage when necessary. These are known as the yellow rooms. Here, extremely intelligent, fully automated machines are used to apply the light-sensitive layer of lacquer to the oxide on the slices and to expose the slices. Yellow light is used in these rooms, as the lacquer is not sensitive to this. The patterns on the masks, a kind of photographic negative, are of course designed by our own development engineers. The templates themselves are made by other specialists. In these so-called implanters, specific atoms can be shot into the unprotected areas of the silicon to give them a positive or negative conductivity. This is done incredibly accurately. For example, 1 atom in 100,000 silicon atoms. One of the next steps in the process is etching, removing material locally from the slices with great accuracy. This department uses an automatically controlled process involving acids and caustics. Another technique used is dry etching with an etching gas. This picture gives an impression of the technology involved in this dry etching. All of the process steps we've seen, and many, many more, are repeated until the product has been fully assembled. This is what the smallest parts look like through a special electron microscope. Sometimes, the chip designers use a technique in which the chip is sawn through, so you can even look inside. The last step in the process involves making connections between the various elements in the silicon. These are so tiny that a minuscule vacuum-deposited layer of aluminium is required to make them. The innumerable processes, which take approximately 3 weeks to complete, are concluded by an initial visual inspection. Each chip is checked for a number of essential functions. After testing, chips which do not comply with the specifications are marked with an ink dot, so they'll no longer be used. Once they've been tested, the chips are ready for assembly. First of all, the slices are laid on a layer of adhesive film and then almost sawn through in 2 directions by a special, amazingly accurate sawing machine, so that the chips are almost separated. The slices are then carefully packaged and sent to the assembly centers in the Far East: Bangkok, Hong Kong, Manila, or Kaohsiung in Taiwan.
The 2008 HS Plus is laid out to produce 13,000 units per hour. This dramatic increase in speed is the result of Essex's new ultra-fast vision system. The optical bond centering guarantees the highest placement accuracy. The integrated quality control offers users an overview of product quality in real time. The integrated flash illumination provides stable and uniform light and enables quality control with virtually no loss of speed. The application range of the SEC 2008 HS Plus consists of a broad spectrum of substrates and lead frames. It handles thin dies, stacked dies, wafer backside lamination, and BGAs. The 2008 HS Plus processes dies right down to 10 mils and of any known design. It handles wafers of 6 to 12 inches in diameter. The HS Plus incorporates either an extremely fast programmable showerhead dispenser or the programmable pneumatic dispenser that enables pattern changes without mechanical adjustments. The flexible machine concept offers users the widest range of processes. Another speciality of the SEC 2008 HS Plus is the thin die capability, covering various pickup processes, such as this multi-needle technology. Here are more of the wide range of applications. This new platform inherited everything that made Oerlikon Essex Semiconductor the leader in die bonding.